know, I just wanted to travel. I was just really curious. My dad was never shy about letting us use the tools, make stuff, break stuff. We spent 5 years then developing the next sort of generation of hybrid rocket motors, and some of them got pretty big to break the European altitude record. So yeah, the real question became, well, this technology that we've developed, how can we make it apply to CubeSats, and how small can we make it? The US government is spending $7 billion a year at the moment in hypersonics research programs. They typically buy the full propulsion system. It's because our technology is unique in that it's non-toxic and it's much more cost effective. The next step is to build the vehicle that will be able to fly to 100 kilometers altitude and be the first vehicle to fly to space twice in a day.
This is Mark Pawlikowski, and welcome to the TechMates podcast, where my partner Henrik and I explore how Kiwi and Aussie founders are reshaping the future and what sets them apart. Henrik and I have been part of successful companies in Silicon Valley and Europe, and now bring that expertise to partner with entrepreneurs in Australasia. By sharing the personal stories of successful Kiwi and Aussie founders and how they got here, we hope to inspire you to dream big. This is TechMates, bringing an outsider's perspective to the stories of those daring to disrupt down under. Let's dive in.
All right, Stefan, thank you so much for joining us on TechMates.
Yeah, no, thanks for having me. Pleasure to be here.
Awesome. So you're the founder of Dawn Aerospace, a really exciting company out of Christchurch. I was just saying we had a Mark Rocket from Rocket Lab on yesterday, so we have kind of like a Christchurch week, I feel. But yeah, we want to know about how you kind of came up. You grew up in Christchurch, is that correct?
No, actually, I grew up in Hamilton. So I was born in Wellington, grew up in Hamilton, just went to school there, like all the way through to high school. But then actually, did my postgraduates, like my undergrad and postgraduate in the Netherlands.
Right. Wow. How did you end up there?
Yeah, so it was kind of an interesting, bit of a funny story. Like I finished school in Hamilton at 17, and I wasn't really ready to go to university in the sense that I don't know. I just wanted to travel. I was just really curious. I'm dual citizen, Dutch passport holder, as well as Kiwi, of course. So it just seemed like it's just really easy to go to Europe and just go get a basic job there, do something, and just go, like I felt like I had an extra year up my sleeve because I was younger than all of my peers at that point. So I wasn't really desperate to go to university.
Was that because your parents are Dutch? Are they from the Netherlands?
So one side of my family, my grandparents immigrated to New Zealand in the 50s.
Do you speak Dutch?
Not well, not as well as I should.
Yeah, but spricht tatsächlich Deutsch.
Yeah, genau. Yeah, so my German's pretty good, but we can get to that though. So so anyway, like 17, didn't want to go to uni yet. Decided I found a good job in Germany teaching English in kindergartens actually. It was like a little private company doing it, just a couple people. And so I joined that as kind of like the native English speaker. So they would speak German, I would speak English to the kids. It was like 3 to 6 year olds. Awesome environment to learn German. So I did that for.
Where was that in Germany?
Really close to Bonn. It's a little town called Siegburg.
Oh, no way.
So,
I grew up very close to there. So
yeah,
that's awesome.
Yeah, like a really nice part of the country as well. And quite close to the Netherlands, so I could go and visit. Like I have lots of second cousins and stuff in the Netherlands. So it was good to like be able to make contact with them. And I very quickly became quite settled in Europe and quite happy with that. So I had a return ticket to go home after 9 months of being there, and I just didn't take it because it was like, why? I don't want to go back. This is like, I've got a great job, I've got cool friends, and I'm earning money. And why would I go to Canterbury University now? Like, I don't need to. I could do that later.
And you were happy, like just being a kindergarten, like language teacher. That was cool.
Yeah. I mean, I was earning great money. I was able to travel around Europe a lot. Learning language, like that was a big deal for me. So just great opportunities in general. I didn't really once again, I just wasn't desperate to go study. After about 18 months of that, I kind of realized like, hey, maybe I'm not going to be an English teacher for the rest of my life. This is going to get boring at some point. I should probably go start studying, but I do want to stay in Europe. So I started looking around, like figuring out, okay, how am I actually going to make this work? And my German was pretty decent at that point after being.
This is just from talking to kindergarten kids?
Yeah. I can talk to you for hours about animals and all that sort of stuff, but I wasn't super confident in my like technical German, like formal language, written and writing. Absolutely terrible because I've never had a German lesson in my life. But like
they hired you to teach English and instead you learned German.
Yeah, exactly. And I'm still the one getting paid. This is a great day.
That's so funny. Did the kids learn the English?
Yeah, they did. They
Did they
don't
pick
play
up the
that.
Kiwi accent?
Yeah,
Are there
little.
like a bunch of Germans now running around with the Kiwi accent because you taught them that?
Well, I would love to say my lessons were that good and it stuck that well, but I'm not sure it did. No. But yeah, so that was a lot of fun. But then I figured I didn't really want to study at a German university. I didn't want to study in German, and like bachelor's degrees all start in German in Germany. Makes sense. But in the Netherlands, they had like aerospace degrees starting from day one in English. So they would run like a parallel Dutch and English for the first year. And then after that first year, it all went English. So
Oh,
that was obviously a pretty good option for me. Being a Dutch passport holder, I could also get all of their like study financing stuff, and I could be treated as a essentially as a local because I was, even though I'm totally not. So that just seemed to make total sense, and it was literally the only university I applied for. I got accepted, and in hindsight, I absolutely can't believe that I did get accepted because
why?
I mean, my grades were fine in New Zealand, but nobody knows what New Zealand grades mean. Like, my graduating mark was achieved with merit. What does that mean? So I came up with some bogus scheme of how my grades translated into a German system and then presented my mark. Like, I think I came up with some number like a 2.6 or something in the German system, I think is what my grade was. Who knows how correct that is? But
Wait,
anyway,
so what is that? Out of what? Out of five or out of three?
Hendrik, you're probably better placed to explain the German school
Yeah.
system than me.
Yeah, so 1 is the best, and then 6 is like you failed, basically. But these translations are, I think this is really how you can hack the system in Europe. So if you come from a different country and you try to translate your grades, they always turn out to be better. My wife got her high school degree in France, and it's pretty good. But when she translated it into German degree, she has like the best degrees. So I think that's how you can get into a university there.
Wait, but why did you translate in a German system if you were studying the Netherlands?
Because they understood a German system, I guess. Like, they took tons of German
Huh.
students. So I guess why didn't I translate it into a Dutch system? Because I really didn't understand a Dutch system and I didn't have any Dutchies around me to tell me how to do it. But I was
Uh,
hanging out with a bunch of Germans, so it seemed
so
like the obvious path.
you like hacked it several different ways.
Yeah, yeah, exactly. Just the right level of confusion for them to accept me.
And
Damn.
so you studied aerospace. Was that always something you were interested in?
Not specifically, as a kid, I was always into building stuff especially with my older brother James. We were always in the shed building things. My dad had a massive collection of tools that he had from his dad. My dad's quite a decent carpenter in his own right. So, he always had the mentality of like, um, you know, give us the biggest saw you can handle type thing. Like, always wanted us to do as much as we could. And, if we cut ourselves or whatever, that was part of the learning, right? So he was never shy about letting us use the tools, make stuff, break stuff, and just, yeah. So like we had a fantastic childhood building go-karts and catapults, trebuchets and massive slingshots and bows and arrows, and like we were just constantly making stuff.
What was the coolest thing you remember building?
Probably the one that I was most proud of in terms of like its actual capability was about a 2 meter tall trebuchet. It wasn't like a counterweight trebuchet like you pull down on a rope for it. Two people pulling down on a rope could throw a decent sized grapefruit. We had a big grapefruit tree. It could throw a grapefruit about 150 meters. Like
Damn.
it'd be in the air for like 25 seconds, and it would just shatter when it hit the ground. So we'd fire this thing over about 3 neighboring properties, over a big school boarding house onto the middle of the school cricket field, and it would hit. So it would go, um, yeah, like 150 meters over all of these houses, and it would
Wow.
splatter on the grass field.
Is that the school you attended?
It was one that we actually biked through every day. It
See,
was boys high school in Hamilton.
so you'd see the results of your.
Yeah, exactly.
So
So
you were
that was,
always
that was pretty
interested in
fun.
building stuff, and then you figured, might be fun to kind of build rockets and spaceships and that kind of stuff? Or how did you think about that degree?
Well, so Delft was really good with sustainable engineering. So I've always been interested in like energy type stuff, like power stations and I was very into wind turbines. Like I thought that would be a cool thing to do. And Delft is pretty well respected in aerodynamics fields. I think at the time there was some quote about like half the world's wind turbines, like the aerodynamic design of those wind turbines was done at Delft University. So I thought that was pretty cool. Good enough reason to go there.
Why are they so good at it?
Long history of it. Fokker aircraft developed in the Netherlands, like that's 1920s. The university developed, like the aerospace university developed around Fokker aircraft. And yeah, I suppose it's just a pretty long history of doing it. But yeah, I got to university and there wasn't really all that much to actually do with wind turbines. Yes, you could get into aerodynamics, but actually it's really just hardcore math. And I'm not particularly intrigued by hardcore math. So I didn't actually gravitate towards that, but I did find this local, like the rocket building student club called DARE, Delft Aerospace Rocket Engineering. And that was a very practical group. It was about 50 to 100 people. And they had like an entry-level program where you came in and 1 year you'd build like a rocket and you'd fly that to a couple K altitude and try to recover an egg. That was kind of like the entry-level program.
Wow.
So I did that, and that was tons of fun.
Wait,
like
that was like part of the
us.
course, or that was just like an extracurricular?
But this is all extracurricular. Like there's no course credits associated with DARE at all.
Okay.
But that was kind of like my first exposure to this student club, which was just a ton of fun and really fun people. And because it was totally volunteer organization, no credits associated with it, very small amount of support from the university, but like a few €1,000 a year type thing. And it was really like self-directed and self-guided. And so at the end of this program, there was a group of us that was like, hey, let's develop some new types of rockets. Like there were all kinds of ideas about developing hybrid rocket propulsion as a newer, higher performance way of building rockets that was still very accessible for students. And the point of doing that was to get higher performance systems so that we could go break altitude records. So the previous generation of DARE students had broken the European altitude record a couple years prior with a rocket called Stratus.
Wait, so what does that mean? Is that altitude record just for students, or an altitude record just like? Because I assume like.
Yeah, just the student record. Like
okay.
So I think that was like 11 kilometers or something. Like it wasn't.
And was there any kind of like constraints on like how big the rocket is? Like I assume launching something small is much easier than launching a bigger one, right?
Yeah, exactly. Like, the gnarlier your rocket gets, the harder it's going to be to launch, as in you're going to have to go further afield. So this student group went all the way to Kiruna in Sweden. There's a like a launch site called S-Range. So like you have to drag all your crap all the way to Sweden, the northern reaches of Sweden, just to launch this rocket.
But you're actually allowed to just launch it. But I guess you have to do a bunch of paperwork to kind of get the permissions and stuff.
Yep, a bunch of paperwork, and it's expensive, and scheduling, and their rocket was a solid rocket motor, so it's an explosive device, so like transportation of that is really, really hard.
Wow, okay.
How's the bureaucracy in Europe for getting a rocket launched?
Pretty stifling.
Really?
Yeah.
So it's true.
So, yeah, oh yeah, that's totally true. Like that's not Europe's strong suit.
Is that because there's a bunch of countries involved and like you're going across borders, or like the Netherlands was just?
Yeah, and just a lot of people, like, they have to be relatively strict on regulation because everything you do affects millions of other people, like especially in the Netherlands, right? Like that area around Delft is one of the most densely populated areas in the world, like from Amsterdam to Rotterdam, Belgium, like there's tens of millions of people.
Yeah, when you said you were launching a rocket in Europe, I was literally like, where can you possibly do that? Because that whole area around Netherlands and where you did your kindergarten job is so densely populated. So yeah, Sweden, Norway, that kind of makes sense for me. But yeah, it's not like New Zealand. Yeah,
exactly. So we spent 5 years then developing the next sort of generation of hybrid rocket motors, and some of them got pretty big. But we ended up building it for Stratus 2, like the next generation rocket to break the European altitude record.
So wait, so your whole idea was like, we're going to break this record by having a different type of engine, or what was the? Yeah,
so the previous engines were this what's called like sugar rocket motors, pretty simple, like potassium nitrate and orbital mixture. But it's kind of like almost like a smoke grenade type mixture. It works, but it's not particularly high performance. If you want to fly higher and faster, going to like a more exotic combination or like a higher performance one. Like for solids, that would be like ammonium perchlorate that you would use. Like that's what regular, like the solid rocket boosters on a space shuttle or whatever would use an ammonium perchlorate. But it's really hard to get, especially in Europe. Like in Germany, you basically can't make solid rocket motors at all. Getting ammonium perchlorate in the Netherlands is really hard, and it's definitely much more dangerous to work with. So it's not really that good idea for students to do. Some do it, but I wouldn't highly recommend it. But the much easier option is to build a hybrid rocket motor where you have a solid fuel and then a liquid oxidizer. And that liquid oxidizer we chose is nitrous oxide because it's self-pressurizing and it's pretty commonly available. The university could just order, 50-liter gas cylinders of this stuff, and you could put together a rocket motor, which is pretty simple machined parts. Make a wax or a sorbitol like fuel charge called a grain, and then you would light a little fire in the chamber and then inject in a bunch of nitrous, and it burns and comes out really, a really fast jet, and that's a hybrid rocket motor. That's literally all there is to it. And then as soon as you want to stop it, you just turn off the nitrous. So it's pretty reasonably high performance. Like you can get quite decent specific impulses out of this, quite a lot of thrust, but it was really simple technology, like very accessible for students.
So you're saying basically like previous guys had done like completely liquid fuel, and you're saying that's like kind of dangerous and like hard to come by. What you guys decided to do a hybrid of solid fuel and nitrous oxide because it was sort of easier to access, but also seems to have more power to it.
Well, actually, most students we at the time were mostly using solid rocket motors. And like, yes, you can go to full liquids, and lots of student groups are doing that now. They're just way more complicated. So like, it just requires a lot better understanding of rocket motors to do that. Student groups are getting there nowadays, though. That was a bit ahead of our time back then. So hybrid was kind of like halfway to the real rocket motors of liquids.
Are all the real rocket motors that are like sending stuff to space, do they all use liquid?
Well, almost exclusively now. Like solid rocket motors are mostly only used for boosters, if at all.
Why is that?
Just the performance you can get out of a liquid is much better. It's also much more controllable. Propellants are much cheaper. Like LOX methane is very, very cheap. Like raw propellants compared to like ammonium perchlorate and aluminium powders, and the binders, HTPB is like they're all really expensive chemicals. And then you're dealing with this massive firework that as soon as you light it, you can't stop it. So they're just much less controllable, much less safe. Like you're never going to build a reusable Falcon 9 style rocket using solid rocket motors. That's just insanity. So, space is trying to work its way towards reusability. And so you need to start thinking in that context. So liquid propelled motors they're just much more familiar in the reusable context.
Take me through like the history. So when the Soviet Union like first launched, Sputnik and then when the US did the Apollo program, what types of fuel were those rockets using? What types of motors were they?
So lots of the really early stuff was all derived from like missile technology. So then there were two primary types of technology, which was solid rocket motors and storable liquids, and then cryogenic liquids. So the V2 was cryogenic liquid, as in LOX. Alcohol is not cryogenic, but the LOX is. So that's like you've got to load it. Yeah, the V2. Like the first ballistic missile, like the German missile that launched from France over to England. So lots of missiles were then derived from the V2. Like lots of the American program was derived directly from the V2. If you look at like a Soyuz rocket, which is the Russian rocket, like that, you can still see bits of the V2 in it, like in the engine design. Like you're like, oh yeah, that's very V2-like. Like the way that they drive the turbo pumps, the way that they, like the combustion chamber design, all still harks back to those very original boosters. But yeah, anyway, so there was kind of like these three different classes that came out. Storable liquids, which is like hydrazine, nitrogen tetroxide missiles, like they're great because they're liquid and very controllable, but they're totally storable. So you could have them completely loaded, sitting in a silo somewhere, and within a minute you could launch them. But all the cryogenic stuff was higher performance, it was better, but not nearly as responsive. So it didn't get used for missiles later on so much. And that's what really became like the primary way to get to orbit for astronauts and for cargo and stuff, all became this cryogenic liquid.
What does cryogenic mean? Is it frozen or something?
Yeah, it's just really, really cold. Like liquid oxygen is only liquid at minus 186 Celsius or something.
Oh.
So, that's fine in a dewar. Like you can keep it in a cryogenic storage container for quite a long time, like days, weeks even, and a little bit just boils off. It's not a big deal. But as soon as you put it in a rocket, which is like a super lightweight optimized structure, there's no insulation or anything on that. It starts boiling off really quickly. So you might lose like, even in quite a big rocket, you might lose 1% per hour. So, and you really need every last percent of fuel in that rocket to make it work. Like every percent matters. So you can't just fuel the rocket and then leave it on the pad for an hour. Like it won't get to orbit anymore. So that's why SpaceX like does now like what they'd call load and go. Like pretty much as soon as loading is done, like they launch within a couple of minutes of that because
So
they just want every last little bit.
they're using cryogenic stuff now, the liquid stuff.
Yep, like Starship uses exclusively cryogenic propellants, like liquid methane, liquid oxygen are both cryogenic. So
Okay.
it's not because they want it to be cold. It's just that's the temperature required to get the properties of oxygen.
Right.
Because they don't want gaseous oxygen. It's just not dense. They
Yeah.
want
Hey,
nice dense liquid oxygen.
does that mean that like it'll be much easier to launch stuff from space because it's like naturally cold?
It can be, but it's not. I think that's a little bit of a like misunderstanding that space is not naturally cold. Like if you put just a sheet of paper out in space and the cold, like the side looking out to space, like yes, that's cold, but the side looking to the sun can get hundreds of degrees Celsius because it doesn't, like there's no convection, there's no conduction away because there's no atmosphere. So there's actually like the methods of getting rid of heat aren't usually there either. So you're entirely dependent on like radiative cooling. So like radiative heat sources are quite effective actually. Like, being in the sun's really damn hot in space.
Yeah.
Interesting.
Before we digress into space stuff, just curious about the student group. So you worked 5 years on this rocket, and did you actually manage to break that altitude record?
Yeah, we did. So it was like a 1.5 ton thrust engine. We built that. It actually took us 2 attempts we went out to the launch pad, which was in the south of Spain, like close to the Strait of Gibraltar. So we launched out over like the Mediterranean. It was about I can't remember exactly now, 200 odd kilogram rocket, so pretty decent size, but over 5 meters tall. And yeah, that eventually flew to 72,000 feet, like 21 kilometers altitude, up
Wow.
2.5.
So you like doubled the previous one almost, right?
Yeah, exactly. Like the original goal was to go to 50 kilometers, so we definitely didn't go as high as we wanted to. But
Still
the
pretty good.
old mantra, like shoot for the stars and maybe you'll like land somewhere near the moon, is not necessarily a bad thing.
So what was that feeling when you managed to do that? Like, I imagine this launch can be quite emotional, right? When you actually like work on it for 5 years and you finally get it into space, into 21 kilometers.
Yeah. Oh, totally. Like, incredible feeling. And can actually, you could patch in like some video of that actual launch because it's all on YouTube.
Really?
Yeah. So I was the pyrotechnician for that. So I was the one of the people that had like the keys to launch, like, and you put the key in the launch box and activate the rocket. And then when you get the command from like the central control, like I actually pushed the button on it to launch the rocket. And so it's definitely it's pretty intense situation.
So you worked on it for 5 years, and then that was towards the end of your university's years that you launched it? Were you already in your
Exactly.
master's?
It was like that. Yeah, exactly. I was in my master's by then. That was like September, and I graduated in November that year. But yeah, it was an awesome feeling. Like it was super exciting to like finally, after many years, get this rocket together after trying to launch it the previous year and failing for other reasons, and we got it back out there, and then we launched it. But it was also like 2 minutes of fun going up, and then 10 minutes later, it's back on the ground. The booster separated out, and that just crash landed into the ocean, and like that's gone. So that was kind of like the bit that I had been working on was the engine, and that was like, well, it's the last time I'm ever going to see it. It's gone now, and it would take thousands of hours to rebuild this thing. It was like, yes, it was really cool, but God, that was a really hard way to reach 20 kilometers altitude, and kind of a bit of a shame, like kind of like a feeling of there must actually be a better way to do this. So somewhat bittersweet in some ways, but awesome way to like get to know people, build a team, set goals, try to hit them, try to figure out what to do when you don't hit them, have to go raise money to do this. Like the university gave us facilities, but they didn't give us money. So like we did have to go raise our own like in-kind sponsoring from local companies as well as actually
Wow.
raw cash. Like we did have to go raise, I can't remember how much it was now, but I think just like the launch site cost was something like 40,000 euro. So it was like, it
Wow.
was really serious money for students to figure out how to
Yeah.
get.
How
So
did you raise that much money? Who would give you money to launch, to basically like launch a rocket in space and then have it just crash down and be destroyed right away?
Yeah, I'm curious about the pitch. Like, hey, we're going to just launch this, and 10 minutes later, it's just going to crash into the ocean.
well, I guess the pitch was we're innovative students who want to do something really hard. We want to progress Europe in this field. So why don't you help out some students and maybe one day you'll be able to hire us? So that it was like MLR and Dutch Space, which I think is now part of Airbus, and but these companies would give us small amounts of money, like it came out of their marketing budgets. So they'd get, they got their logos put on the side of our thing, and we'd thank them every time that we, went and like we wrote a bunch of papers and went to conferences and stuff. So they got mentioned a bunch of times, and quite a few of our members ended up going and working for them. But it's
That makes
just
sense.
their way of like big corporate being able to support innovative small groups. And like in the end, 20 grand here or there for them is not a big deal. So like it was very mutually beneficial, I think.
Cool.
Makes sense.
Very nice. Wow. So that's pretty impressive. I mean, I guess I'm still like kind of wondering like what's so hard about like why didn't the previous students get into that altitude? Like what was the innovation that you guys had? Because I don't really know. Can you maybe tell us about like the science and engineering behind launching rockets and like what goes into like the engine and how that even works?
Like to some extent, it's how ambitious the students feel that they can be.
Hmm.
And I think like the previous team launched in like 2009 or 2010 or something. And back then, like this is like early days of the internet, there wasn't that much information out there on just how to do stuff. Like information wasn't as free flowing as what it is now. So there wasn't actually that many resources out there of how to build your own rocket engine type thing. But it's gotten way more common in general for student groups to develop really quite complicated engines. And even just resources like Everyday Astronaut, like it's a really good YouTube channel that just tells you a whole bunch of really entry level stuff about rockets. Like, and lots of it's actually really quite good, useful information. And it's getting easier and easier to actually do this stuff. Additive manufacturing is also helping a whole lot. It's making it way easier to just go design something in CAD and have it printed, and it more or less works. So yeah, like the technology that students are able to really do now is quite impressive. And I'd say probably the other mechanism is like university and the wider industry's acceptance of students doing this sort of stuff. Like you couldn't just start a student group and say like, yeah, we're going to build a rocket that's going to go to space, because no one will believe you. No one will want to support you. NLR and Dutch Space are not going to give us 20 or 50 grand to do it because there's no basis for them to do it. It's all just pie in the sky crap, right? But if we say, well, the previous group broke this record, we're going to go a little bit higher now, it's all just way more credible. Like it's way easier to get the snowball going. And so the student group after us was able to go raise even more money than we did because they got bang for buck last time. It stands to reason they'll get even more bang for buck this time. So like, you got to sort of stand on the shoulders of giants, maybe is the cliche thing here.
Man, I can't believe I did an economics degree. This sounds so much cooler than what you did in my fucking calculations.
A lot of hard work though. Like I still had to do an
imagine.
aerospace degree.
Yeah,
on the side. On the side, right?
Yeah, exactly. On the side.
This was your full-time thing, and like you just what kept you there as a degree.
Totally.
That's cool.
Cool. So then let's look into kind of your last years in university, and how did you decide to go back to New Zealand straight away? Where you're like, I'm done with Europe, done with the Netherlands?
Not quite straight away, but pretty close to it. So through my master's, I always had to do internships. And so I elected to do an internship abroad in New Zealand, of course. So that was really nice. So I was able to do an internship at Rocket Lab, and next year I did an internship at another aerospace company called Airwork. So that was like a nice way to start going home more. But then, after, like my master's thesis was all about bringing aspects of the technology that we had developed for these really large rockets and trying to make them as small as possible, and for satellite applications. Like CubeSats were a big deal back then. There was lots of theories about how CubeSats were going to be the next constellations. And I did this master's thesis with a company that was already doing lots of CubeSat components, like attitude control systems, cameras and stuff for like star trackers for CubeSats. And so like, they built the systems to allow a CubeSat to know which way it's pointing and then point in that direction. And then the next logical thing was, okay, now can you go in that direction? So you need propulsion. So that was where our product kind of fitted in.
Mm.
So yeah, the real question became, well, this technology that we've developed, how can we make it apply to CubeSats and how small can we make it? So instead of going from the biggest rocket we had built was 13 kilonewton, the question was, could we make it 1 Newton? So 13,000 times smaller. That was basically my master's thesis, was figuring out how to do that. So hybrid rockets didn't work. We had to go to full liquid rockets then. And then we needed a reliable method of igniting these as well. So, we had to go to spark ignition. In my master's thesis, within a 9-month span, we looked at all the different propellants that we could use, came to this propellant combination that we wanted to use, came to the basic design, and then in about 2 months, did 4 engine iterations of build it, test it, this didn't work, this did work. Next one, go back to the machine shop, literally make them myself, solder all these engines together, go test the next one. And yeah, went through 4 engine iterations until finally we had something working at about 4 Newton, which was pretty good.
And this was for a job that you were doing?
Yeah, well, that was a master's thesis with this company. And then that spun into a job with this company, Hyperion Technologies.
In New Zealand or in Netherlands?
That's in the Netherlands. But I told them, I'll keep working on commercializing this technology, but I want to go home and live in New Zealand. So that was kind of like I was home in New Zealand, but I kind of wasn't home because I was working remotely for this other company.
Why'd you want to go back to New Zealand?
Just be closer to family. Like I like Europe for lots of reasons. Great place, great, especially culturally, lots of festivals, lots going on. But just the geography, especially living in the Netherlands, it's just so damn flat. And I really like mountains and snowboarding and stuff. It's really hard to go away and do the types of adventures that I would do in New Zealand, like on a weekend. So I kind of wanted that weekend warrior life back. That was pretty normal in New Zealand.
Yeah, wow, cool. Okay. All right, so you moved to New Zealand, still working for this company, probably have weird hours, working at night, right?
I was mostly working on my own, commercializing this stuff, so that wasn't so much of a problem. They were reasonably hands-off about that. But slowly over time, this was happening then in parallel to us trying to form Dawn Aerospace, because we wanted to commercialize the technology that we had developed for Stratus 2. But we kind of realized that actually this technology, after talking to a bunch of customers, it really wasn't commercializable because it's just it's single use. Yes, it's low cost. Yes, it's really accessible and easy to use for students. But it's all just still because it's single use, it's just too hard. Even if you could do each flight for $100,000, it really wouldn't be that interesting because you couldn't fly that much. If you can only do 10 flights a year at $100,000, this is $1 million a year business. It's not going to cut it. It's going to support 3 people. So the business just.
Yeah, and the group that was kind of initially thinking about Dawn Aerospace, these were all people you were working with in the student group in Delft?
Yeah, exactly. It was founders totally out of that group. We kind of knew that we had a great team, so we wanted to keep that together and we'd figure out what technology to work on. So it was around probably a year before we graduated that we decided we wanted to form a company of some kind.
Oh, okay.
And we had to figure out what technology that would be. And yeah, in the end, we kind of came up with the founding principles being that whatever we did, it needed to be scalable. Really, it had to serve space 10 or 20, 30 years from now. It was very clear that the number of satellites being launched was going to grow exponentially. And that has eventuated, and that the current technologies weren't going to serve that very well, neither for in-space propulsion or for getting to orbit. So yeah, that's why we basically ditched the ideas of expendable rockets and went into reusable. And eventually, it was actually interactions with my brother who had been working in aerospace in New Zealand at this company Airwork that I also did this internship at. We kind of came to the conclusion of all this work that he was doing in aircraft, certifying aircraft parts in New Zealand and then exporting them to the rest of the world. This was absolutely a model that we could bring to spaceflight. There was no reason that we couldn't. certify something that was fundamentally a rocket as an aircraft. And that would allow you to fly it as much as you wanted. You get a single license. You can go fly 10 times a day if you want. The technology allows for it. But that just wasn't possible in rocket world.
Because you're saying the barrier was the certification piece?
Yeah, absolutely. Like licensing and certification is just a nightmare for rockets. It's always a one-time thing.
Wait. So you're saying you need to is this in New Zealand or globally or where?
Globally. Like if you clicked your fingers and had 1,000 rockets, there's no way you'd be able to launch 1,000 rockets in the next 12 months. It's not going to happen. Like you won't get the licensing through. You won't have like launch site availability. Nothing about the setup works. So it's not even like a technology manufacturing problem, or like they are problems, but there are other bottlenecks anyway. So you have to solve those other bottlenecks.
When you thought about Dawn in the beginning, did you always think that New Zealand was going to be a good place to build it because of the licensing and so on? Or did you think about other geographies as well?
The short answer is we knew it was doable in New Zealand. So that seemed like a great place to start. And my brother James was a delegate of the CAA, which meant he had like delegated authority to be able to say what was certifiable or not. Now that delegation wasn't going to like one-to-one transfer to what we were doing, but he already had a very strong standing in this community. We already knew the path to do it. At that point, it didn't really matter if you could do it elsewhere. It was pretty clear you couldn't do that in the US. And that was like the main other market where that could happen, or Europe for that matter. Definitely not happening in Europe. So it was like, well, let's just run with this. And, from a personal point of view, I also wanted to be in New Zealand.
Sure.
We knew that like Rocket Lab was this massive bow wave ahead of us, showing that like aerospace is doable in New Zealand. So let's just ride that.
So wait, so I'm still surprised. So you're saying to launch a rocket, you have to get certification. I somehow didn't understand that. Okay. So you can't just like launch things off into space.
No, you can't just fly to orbit. You have to get sign off from your local government.
But but like, what if you find like some random country, like, I don't know, like do you have this, like if you like kind of rogue take over some part of a country or find a part of a country that's like, no one's like controlling, just like go throw your like rocket into Congo and just like launch from there. Like no one's going to stop you, right?
Yeah. So like, China does what it wants all the time in this domain.
All right.
But,
I see.
like, yes, if you started a company in Congo and the government of Congo was totally on board with not giving a shit about the rest of the world and whatever, then like, yeah, you could, like, right. But other countries are going to start putting pressure on, whatever country is doing this. So like, maybe there's a limited amount of pressure that we, the West, can put on China, but they certainly do put pressure on them when they act in ways that's not in everyone's best interest. Like when there's been, they've created a bunch of space debris a few times. The US has also done that, by the way. But
I see.
There's a whole bunch of liability that comes with launching stuff to space. Every time you do it, you could. International law stipulates that if a rocket launched from New Zealand causes a bunch of damage, say in the United States, that the New Zealand government is liable. So the New Zealand government says everyone in our country who wants to launch has to get a license from us, and that license basically checks to make sure that rocket doesn't actually have a high chance of causing a whole bunch of damage in the US, for example. And if it does, that they have insurance for it, et cetera, et cetera. So like the New Zealand government has to hand this liability down to the actual launch provider and make sure it's covered.
Okay, so you were like, so basically you saw that and you were like, hey, screw this, we're gonna like just use a plane.
Well, pretty much, like more like, hey, if 90% of this rocket doesn't actually have to be a rocket, it can just be an aircraft with the performance of a rocket, as in it takes off from a runway, it's certified as an aircraft. Yes, it probably also needs a high altitude license, but that's fine. Like aircraft can get that. And now it just flies under this license as much as it wants, because this bit of the thing doesn't actually have a chance of, damaging something in Philadelphia.
Why doesn't it? Doesn't it still have the same like risk factors?
Not really, because this bit is never going to go that far or that fast. Like that first stage is never going to do that. So that you can actually separate out that whole bit of hardware from the going to orbit bit of the equation, because you're only going to space. Like the difference between space and orbit is quite large, especially in terms of your like risk areas. So that can be.
There's like being in orbit is like, it's like you're closer to Earth and has less damage potential than being in space. Is that a difference?
Well, like going into orbit means you're going to go all the way around.
Yeah.
So let's say you got 95% of the speed you need to get into orbit, but you didn't quite get all the way. That means you're going to come down, but potentially like on the exact opposite side of the world. So that could be over some other country, right? So like you could hit anyone at that point. But just going to space, like just going up to 100 kilometers altitude and back down again, like your maximum range, if you're only going that high, is like it's hundreds of kilometers still, but it's not 10,000.
Right.
When you came up with this concept, did you already think about the commercial applications for, why would you want to do this basically?
Yeah, so that's a really good point, because like at this point we're totally thinking about getting to orbit, right? Like I want a better way to get to orbit, and that's like an eight to $10 billion market, depending on who you ask. Now, as we've gone on, like zoom right forward to now, we've really refined our philosophy around this is an aircraft with the performance of a rocket, not a rocket with wings. And actually, there's so many interesting applications that are not even getting to orbit. Go back from orbit and you go to something like hypersonic aircraft. The US government is spending $7 billion a year at the moment in hypersonics research programs. So that's just trying to understand the hypersonic domain, build technology that operates in the hypersonic domain. Hypersonics is like, that's literally a fifth of the speed that you need to get to orbit. So this is like a very low performance rocket to get to hypersonics. So it's like, oh shit, we can do that. I can do a very low performance rocket, sure. So, the thing that we built as students went to Mach 2.5.
What is a Mach thing?
Mach is like the speed of sound is Mach 1. So flying faster than sound is supersonic, and then flying 5 times faster than sound is called hypersonic.
Right. So you saw that hypersonic exploration is definitely an interesting market, just to kind of understand the technology. And I guess the US government spends money on it for primarily defense purposes. What's the reason for them to explore that?
Yep, primarily defense, but also just like fundamental science reasons. Like they're just pushing science forward in a whole bunch of different domains. But yeah, like one of the major ones is like missile defense. So like all missiles are hypersonic to some extent because they're basically all based on rocket technology. So they come back from very high altitudes at 10 to 15 times the speed of sound and then slow down through the atmosphere. So there's being able to simulate or like replicate that with a reusable vehicle is really great for them being able to test their missile defense systems to know, like, can I actually detect one of these things? And keeping people trained, keeping people sharp. These are many, many billions of dollars worth of systems. Spending some money to make sure that they're like to maintain that capability is important to them.
Has anyone ever tried that, or like when you guys had this idea, were there other like people trying something similar?
To use like to bring together the performance of a rocket and the business model of an aircraft?
Yeah.
Not really, to be honest. No one's really figured it out. And people keep making the same error, which really astounds me. That everyone, like a lot of people have put a rocket motor in an aircraft, like as in something with wings, but they immediately make a bunch of decisions that just completely destroys the business model.
Like what?
Like Virgin Galactic, for example. Awesome company, awesome people, came from really, really smart people like Scaled Composites, built the first, like Burt Rutan is an absolutely brilliant aircraft designer. But because they chose a hybrid rocket motor, and every flight, they basically have to pull out the entire combustion chamber and put in a new one, because that is like a spent thing. They have to do basically like major aircraft maintenance every flight. So like there's no way that they're going to fly twice in one day. That's just not tenable. So your aircraft is going to be on the ground a lot. So that means you're not going to be flying a whole lot of payload. So
what was the decision you guys made around that? How are you different?
That it like literally everything had to be thought about as it's an aircraft with the performance of a rocket. So if you're doing anything that invalidates it being an aircraft, it just doesn't work. So like cryogenic propellants, going back to that, I don't want cryogenic propellants because that means I'm going to have a time-sensitive launch. I can't just roll this thing out onto the runway and then have it wait for an hour because then my mission doesn't work anymore. So it's got to be storable propellants.
So you guys use like a hybrid approach?
No, we use liquids, but just storable liquids. So like hydrogen peroxide and kerosene. So like there are solutions to all of these problems, like that comes with a small performance hit and a small cost hit, and that hydrogen peroxide is more expensive than liquid oxygen, slightly lower ISP, constrains you in other ways. But then you get this fantastic property that I can land the aircraft, fuel it up, and be flying again like 4 hours later. Like that's amazing. I don't have to do major maintenance every time I fly.
So wait, let's go back to like the use case. So what are the use cases that you want to use something like this for?
Yeah, so like the hypersonics thing, like we're not at hypersonic performance yet, but that would be a great example of like, say there's a US researcher who wants to find out what how's this material going to react to the hypersonic freeze stream, like where you've got crazy amounts of heating going on. When you get to around Mach 6, Mach 7, you start having like the air starts ionizing and doing all these crazy things like breaking down. And like there's just a whole lot of interesting physics phenomenon that happened. And they might want to understand how this material reacts to that, or a coating on a material. But they don't just want to do one experiment. They want to like change 10 different parameters on this experiment. Like what happens if I bake this material for longer? Or if I have a slightly different composition. So I want to do 10 tests, or maybe a matrix of 3 different parameters, 3 different ways each. So now I've got like 30-ish tests. In the traditional test method, you would take an actual like orbital class booster, like a rocket, like literally Rocket Lab does this. They take their Electron launch vehicle, and you can buy a hypersonic flight. And that works great because rockets can easily get to the hypersonic regime. But it's not so great because it's like $10 million a pop. It's $10 million to that test. So if I want to do 30 of them, like, you're talking about a very expensive program. But if I have an aircraft that can just frequently fly to the hypersonic regime, you want to do 30 tests, cool, we can do that over like 2 weeks. Every day you show up with 3 new samples, we'll do 3 flights, you get your data back. Maybe one didn't work, we can just refly that. Maybe you actually want to tune some parameters because you're finding, like it's iterative now, right?
Yeah, much faster, right? Much faster spins.
And just a totally different mentality of testing. Because you can adjust as you go, because the next test is not actually that expensive. So this completely changes how people can think about testing in the hypersonic regime.
Who are some of your customers, and what's kind of the different things they're buying from you, use cases? Are you selling flight time?
Pretty much. Yeah, so that's hypersonics, which is a reasonably decent performance vehicle. The vehicle that we're at now is not actually a hypersonic capability. Like what we've flown is supersonic up to 80,000 feet. And there's already some customers that are interested in using that. And it's a myriad of different things. Some of them want to use it for like satellite technology development. Fly it on this vehicle first, you get to microgravity. You test it in a somewhat relevant environment, but you don't have to take it all the way to orbit.
What is microgravity?
Microgravity is basically being in free fall. So when you're in orbit, you're actually constantly falling. Like that's zero gravity is falling, right? So you can achieve that by being in orbit. Or if you imagine throwing a stone up really, really high, like, if you threw a stone up to 100 kilometers altitude, once it's out of the atmosphere, it's just in free fall. And it's going to do that for about 3 minutes. It'll be in free fall. So during that time, there's no gravity effects. So you can do an experiment as if you were in orbit.
So is it like those planes that, like, I know there's like planes that take you up and kind of like go up and down and make you feel like you're kind of in space?
Yep, that's exactly that. Exactly. It's a parabolic flight, except, they'll give you like 20 seconds, and it's not great quality in the sense that it still bumps around a little bit. There's still some turbulence and whatnot. It's not perfect microgravity. We can get about 1,000 times better microgravity, like 1,000 times less disturbance, and you can get it for about 3 minutes, not 20 seconds.
Is that the same as just like going skydiving? How's it different from skydiving?
Well, skydiving, you do actually feel effects of gravity. You're not actually in complete free fall because you're not able to accelerate, like you're hitting the atmosphere. So, like if you're skydiving holding a cup of water, the water will stay in the bottom of the cup. Like if you turn it sideways, it'll flow sideways out the cup, right? It's not just going to sit. Like there are actually gravity effects because you're not freely accelerating.
And you guys achieve the microgravity by going above the atmosphere?
Exactly. Like the effective atmosphere stops at about 30 kilometers. Like at that point, the air is so thin, there's almost no effect from the air anymore.
Interesting.
I want to go back to when you kind of when you had this kind of concept. I guess you realized very quickly that you need a shit ton of money to build an aircraft, right? So did you start pitching this to investors? What was their reaction a few months and years later?
You couldn't convince companies that you can hire the team anymore.
Yeah. I guess we kind of came together, like Dawn came together as a company that wanted to solve a larger space transportation problem. And there were two distinct business lines to that. There was like the Earth to space problem, and there was the space to everywhere else problem. Like, so in-space transportation is very different to space launch. And we had a product, like I mentioned, about developing these very small rockets that had kind of started within Hyperion Technologies, and that later essentially got spun out of Hyperion Technologies. Like that's a complicated story in itself, but ultimately, Dawn Aerospace became the vehicle to commercialize that technology.
Oh, okay.
And so that was, it's a much smaller problem. It's much more accessible. With about $1 million, we were able to develop the first thruster, about a 20-Newton thruster, which we then...
What is a thruster?
Just a small rocket motor for on a satellite. So this produces a couple of kilograms of thrust, which is enough for like a 200-kilogram satellite to do some small maneuvering around in space. It's not going to take it from the Earth out to the moon or something like that, but it's enough to change its orbit.
Are you familiar with Zeno?
Yep. Yeah, I know Max.
So they do something similar, right? They position satellites?
Yeah, so what they're primarily doing now is like the attitude control of the satellites. Like, I understand that there's ways to turn that into like full propulsion if you have an external magnetic field. So like in low Earth orbit, that works.
I see. So you guys are actually moving the satellite versus they're just positioning it in a certain location.
Yeah, I think they can do the latter at some point. I think that's their intention, but the starting point is the orientation.
So you went to investors basically with this thing that can be commercialized quite quickly, and that is a solution, but it's a much smaller problem. Did you already talk to them about the bigger problem that you wanted to solve with Dawn?
Yeah, absolutely. Like it was all about both, like doing both of these things in parallel. And they were very symbiotic in lots of ways, in that they both require obviously very good understanding of rocket motors, but also just general engineering practice.
And was it easy for you to raise capital for a business like that?
I wouldn't say easy, but we did find a way to make it work.
Yeah.
Starting out is never easy. And the first chunk of money is always the hardest. But yeah, we were very much supported by the fact that we did have some pretty good early traction with the satellite propulsion.
Yeah.
So that really helped. Like there was a customer essentially lined up to start using the system. We had good ties in with the European Space Agency, so there was some good development contracts there. There was early revenue. I guess that, especially along with our experience in actually building systems, breaking European altitude records, there was enough momentum there, enough reason to believe in us as founders that we could do quite hard stuff. And we had a technology that people actually wanted.
So who are some of your customers, and like what are your missions for?
So on the satellite propulsion side, it's about 25 customers all around the world. They're building satellite constellations like Earth observation constellations or communication constellations. We recently had one customer who's doing asteroid mining. So they launched on their satellites now out past the moon. That was a meteorite inspector mission.
On your?
Not on our plane. That's using our satellite propulsion. So they launched on a SpaceX rocket.
I see. Sorry. So you have two separate businesses. You have the launch business and you have the propulsion business.
Exactly. So the propulsion business has given us a lot of early revenue, and we've been able to commercialize that very, very quickly. So that's about it's a bit over getting close to $20 million a year business now.
Just the propulsion business alone.
Exactly. So that's cool. So that's really nice, that we have really good customers there.
And is that like recurring revenue, or is that like one-off kind of?
Like it's project based per customer. So they'll say, "Oh, I'm building 6 satellites. I need propulsion for them," and there'll be a contract specifically for that. But we've had customers come back and say, "It's 6 now. It'll probably be more in the future." And then so there'll be stages to these contracts or repeat buying from customers.
And what is it that they are getting from you they can't get somewhere else? Are they building a satellite from scratch and they just need like your kind of thruster engine component, or is it something else?
So they typically buy the full propulsion system, and so the reason that they buy from us, why didn't they just get this from somebody else, is because our technology is unique in that it's non-toxic and it's much more cost effective, and ultimately they can get the same product much more reliably, much more cost effectively through us. So going back to the reusable, scalable type philosophy of Dawn Aerospace, the propellants that we chose to use for these satellite propulsion systems are just much easier to use at large scale because they're non-toxic. That means, they can test all their satellites, they can put actual propellants in them, and they can launch hundreds of them at a time. And even if one leaked a little bit of propellant, it wouldn't be the end of the world because that propellant's not going to kill you. That one satellite won't work, sure, but it's not going to call off the entire launch.
And on the just back to the kind of aircraft part of the business. So that's obviously kind of I understand, a much bigger moonshot. And one of the probably biggest applications might at some point be defense, as far as I understand. So I want to talk a little bit about how you think about this, because we had some conversations in the last few weeks with founders who are building stuff, and now kind of in the last 1 or 2 years are realizing, there's actually a big defense industry that we can serve. Some of them, felt more or less comfortable with it. So would love to hear your view on, do you think this should serve defense, and how do you feel about it as a founder?
Yeah, firstly, yes, defense is an application. I'm not sure it's the main application. We still lean pretty heavily into civil applications, but defense does have a role to play. So because of the technology direction that we've taken, where everything is very rapidly reusable, yes, there's a useful tactical element. Rockets are never going to be particularly good at taking large payloads compared to traditional aircraft. So, and because it's rapidly reusable, this is not like a single-use device. It's way too well equipped and expensive to use as a single-use device. So this is very good for reconnaissance. It's very good for testing missile systems. It's not very good at delivering ordnance. So already from a product direction, it's pretty clear where in a defense realm we're going to be useful and where we're not. And we don't need to compete, and we're not going to try to compete in those areas where it's not useful. And aside from that, I personally don't have a desire to go really deeply into the pointy end of the spear type applications. I think that's just not really who we are. And it's not really part of our core philosophy. And there's plenty of other companies doing that really, really well. Where I see the big opportunity is really leaning into the rapidly reusable side of this technology. That's the real difference, right? Regular rockets are single use, are very expensive. Can we do the same thing, 1,000 times more at 1/100th the cost?
And Stefan, but how do you sort of think about the two different sides of the business? Aren't they pretty separate and pretty different applications, different use cases? It sounds like one has a lot more revenue than the other one. Thrust your business.
Yeah, absolutely. And they are, in some ways, they are diverging, at least in the short term. In that the customers that we're seeing for the aircraft are quite different to the customers for the satellite propulsion. The original theory was that in the end we would have an end-to-end transportation system where one customer would be able to take a ride to space and then also be able to use our propulsion in space. And there would be a lot of synergies in considering that entire transportation problem as one problem. You can build a more efficient transportation system by doing that. That's definitely still the case. It's just that synergy is probably still 20 years away before we really are actually building orbital class, space planes, not necessarily single stage to orbit or anything, but it's just becoming really clear that there's actually a ton of very interesting things to do with a rocket powered aircraft long before you even get to orbit. You don't need to go all the way to orbit. Microgravity is a really interesting thing. Hypersonics is a really interesting thing. Actually, if all the reasons that you did go to space can be achieved with something that doesn't have to go to orbit, that's actually much better, much more cost effective.
Interesting. But do you see yourself kind of just focusing on one side of it, or do you continue to pursue both? Because it's always hard to keep focus, right? I'm sure you have different priorities in the company that kind of vie for your attention, for resources. And if one's bringing more money or product market fit, it always just feels like it's easier to just focus on that one. Why keep this other one going?
Yeah, so it's reasonably natural for aerospace companies in general to diversify. You can say the same thing about SpaceX or Rocket Lab or Boeing or Raytheon or whatever. They're all highly diversified companies. They actually tend to diversify almost as fast as possible. But there's pluses and minuses to both. I absolutely agree that having focus, especially for a startup in an early stage, is really, really valuable as well. So we have to get very disciplined about that. And we're already internally changing our structure to ensure that there is the right amount of focus on each thing.
And what does the next 5-10 years look like for you, both in terms of products that you're building, market opportunity? What will Dawn kind of be known for?
Yeah, so let's just stick to the aircraft side because that's certainly the easiest to explain this. It's basically about just expanding what you can do with aircraft. Going back to the commercial realization that this is an aircraft first, but with the performance of a rocket, we need to start from aircraft type things, start serving those markets, serving those customers. Released today that we have a commercial payload license, so we can start flying these early customers that we have, and there'll be announcements in the future about us actually flying them over the next 6 months. So that's really cool. Like that's an exciting next step. And then technology-wise, it's we're already flying supersonic up to 80,000 feet. The next step is to build the vehicle that will be able to fly to 100 kilometers altitude and be the first vehicle to fly to space twice in a day. That'll also fly to Mach 3.5. That's starting to get really interesting for people who want to do like high-speed flight sciences, who want to do microgravity research, develop new cancer and liver treatments in microgravity, or new semiconductor materials, or like there's all kinds of really interesting applications within there. And then we can build the next generation vehicle on top of that, which will be then like truly Mach 5 capable. We'll probably fly to more like 150 kilometers altitude, even more microgravity time, more payload, better serves these customers. We just continually expand what you can do with rocket-powered aircraft.
And then on the other side?
But the other side is really just continual iteration of our product. So basically every customer we sign is asking for some sort of modification or some sort of improvement. We started with satellite propulsion in low Earth orbit. We now have customers that are going out to the moon. I mentioned before we have one going out to asteroids. We're continually getting more and more demanding customers that want higher reliability, who want more redundancies in their systems, bigger systems as well, like larger thrust engines. So we started with 20 Newton, and then 1 Newton was our best selling. So we're now developing a 200 Newton thruster, developing larger and larger systems for just larger satellites, and soon out to geostationary platforms as well. So then you start talking about like needing real radiation hardening so that they can just deal with this quite extreme environment of space.
And when you sort of say that, like, I guess help me understand, is it that every satellite will have your thrusters? Is that kind of like the end goal? Are you like the Intel chips kind of powering all the different, computer providers? Is that kind of the way to think about it? Or kind of an analogy for where you want to go?
Yeah, exactly. Like ultimately, like everyone building a satellite constellation needs to put satellite propulsion on there. They mostly use electric propulsion now, which is quite slow. It's very efficient, but it's very slow. So they're not very responsive to needs to change, say, if a satellite breaks or...
How does electric propulsion work?
It's essentially you have like an inert gas that you can ionize and then accelerate with an electric field very, very quickly. So like an ion thruster or a Hall effect thruster are the most common types. But you're essentially using electricity to accelerate a gas. So like you also run out of propellant eventually. Like once you run out of that reaction mass, then you're done. But it's just that you can accelerate that ion much faster than what rocket thrust from like a chemical rocket would be. So they're typically 2 to 3 times more efficient than a chemical propulsion system.
I see. So actually, that's a good question. So whenever you guys provide somebody with the thruster and put it on their satellite, they're using some kind of liquid fuel. Doesn't it run out at some point?
Yeah, exactly. It does run out. So that's kind of the next game, is actually figuring out refueling. So yes, satellites run out. Can you refuel them? Because then you can recover your whole asset, right? And fuel becomes an operational cost rather than like a life-limiting resource. So that's also one thing we're working on. We're starting to integrate like a refuelable side to our propulsion system. So we have a few customers who are going to use that as well. And then one day you'll be able to actually get refueled by like a Dawn satellite or another satellite. So that's still a long way away.
How do you feel about
coming.
How do you feel about the kind of space industry overall? So there seems to be like this big commercialization moment in the last, let's say, 5 years or so, right? Do you think we're kind of at the beginning of this exponential curve, or where do we think we are?
Yes, we're definitely at the beginning of an exponential curve. Like we're just starting to get real mainstream value out of space. Like I think Starlink is the first thing from space that everyone really understands the impact and that it's really, really empowering. But I would say GPS is probably the first thing that was actually really impactful. It's just that most people didn't realize it. Like it was almost like so under the radar that people didn't realize that Google Maps and them driving down the road is powered by a satellite thing. So but Starlink's like, it's satellite internet. Oh, cool. People get it now and they're like, oh yeah, I'll pay $100 a month or whatever for satellite internet. So that's the real like consumer impact it's just coming to fruition now.
Do you think in like 5-10 years, most of the internet will be satellite internet?
No, I don't like. It's pretty hard to compete with pumping data through a fiber optic cable. Like that's just a way more efficient way to transfer data. But the entire market of transferring data is huge. I have no idea what the actual number is, but even a small fraction of that will be done over satellites because it'll be a remote place that there's no point in making a fiber optic cable to the middle of some mountains or to the middle of the Pacific Ocean. Like satellite data is going to move, like satellite connectivity is going to move a small fraction of all data. That's still crazy huge amounts of value for space. Like space is a really small industry. It's nothing compared to pharmaceuticals or agriculture or like worldwide logistics or whatever. Like those are all multi-trillion-dollar industries. Space launch is a lowly $10 billion and all space manufacturing and everything is like 400 billion or something. I can't remember what the number is. But it's
Are you one of the biggest companies in the space industry? If you were to look at like, I don't know, yeah.
Dawn? No way. No, we're
No?
still a tiny startup in the grand scheme of things.
Hmm.
But it's surprising how fast these things can change.
Uh-huh.
As in, SpaceX was a nothing company 20 years ago. Like it would literally just barely started.
Uh-huh.
And within 20 years, it's now 80% of the world's capacity to space is SpaceX.
So it's
What is it about like space more concretely? What are the so like GPS I get, satellite internet I get. What are the other applications that are going to create space into like this huge industry?
Yeah, so like Earth observation, like powering weather data and all that is huge. Connectivity in general, I think it'll get a lot bigger than people realize. So like yes, it's a small thing now, but it's going to get to be much, much larger. Some things that can get very large that are nothing yet is things like in-space manufacturing. So that's where there's very special materials, very special drugs that you can manufacture in microgravity because the physics is just different in microgravity. You don't have convection happening because you don't have gravity forces to drive convection currents, basically. So that means crystal formation and protein formation is very different. You have things like surface tension effects drive how fluids move rather than convection and whatnot.
yeah,
So end effect, you can potentially make fiber optic cables that are way better. You can potentially make semiconductors that are much more efficient. You can potentially make new types of liver disease treatments and cancer treatments. There's whole startups working on just like each of these small niches.
And
do you think
we're going to see? Do you think you're going to see like an explosion of early stage activity in space? So like us as investors, should we expect more deal flow in space tech? Do you think?
Like generally, yes. I think that has been the trend over the last 5 or 10 years. Like there is more and more stuff happening there. It's somewhat driven by space access, as in these companies need access to space to be able to run these startups and run these experiments, right? So it's somewhat related to that. Companies like Rocket Lab and SpaceX, once again, have really driving down the barrier to accessing space. We want to bring that to the next level again by driving down the cost to access suborbital space so you can do even more faster experimentation and iteration. But yeah, like if a great place to look is like what universities are working on now. How are they, like, what are they trying to do with microgravity now?
Uh-huh.
And the really interesting things that are kind of on the horizon.
Yeah. And in a way, you and SpaceX, you kind of creating the rails for people to kind of, launch stuff and build. So now that barrier has become lower, people can actually kind of build commercial opportunities.
Exactly. Now, I will say, like, lots of this is still very early stage, though. Like, people are not even sure of what's possible. Like, it's kind of like the internet in the 90s. Everyone's kind of like, I think this is going to be a big thing, but nobody's able to point to right now, like, is it going to be Facebook or is it going to be Instagram or is it going to be an Amazon or like, I don't know how, like, what fraction of companies died in the dot-com boom, but like there will be these big clearing events as well. Like there are lots of ideas that just turn out to be bad ideas, and I think that's natural. So we should expect a lot of failure as well.
Where do you see what industries do you like? If you're advising us on space and investing in space, what kind of industries, what kind of opportunities do you think we should be looking for? Specific industries, customers, specific areas?
I guess it really depends on like your risk reward. Like we Dawn as a company, like we see ourselves as investors in space as well, right? Like I could go work on something completely different. I could go work on fusion technology if I thought that was a great bet. So why work in space in general? And if you're working in space, what do you think you should do? If we're talking about that latter question, if we've decided space is a good idea, I like the idea of working on something that everyone is going to need. Like, I think it's hard to imagine a space economy that doesn't need to move around in space. So, hey, in-space propulsion, probably a good idea. Let's work on that. If we just build the best in-space propulsion, it doesn't matter whether you're a comms satellite or whether you're doing asteroid mining or whatever, like you're going to need in-space propulsion. So you're probably going to need to get to space. Now, so launch vehicles also going to be important, right? So space transportation is kind of like just the absolute underlying infrastructure of this industry. So work on that, sell picks and shovels. Maybe you won't make the most money of anyone, but it's a very reliable bet at this stage. It's kind of like betting on Cisco in the 90s, like network switching. I don't know what the hell the internet's going to do at that point, but the more and more data it transfers, the more switches people are going to need. So Cisco was probably a really good bet in the 90s, as opposed to like an Amazon or something like that for pets.com. I think was the other classic.
Yeah, Nvidia for AI, right? That's kind of what everybody
Exactly.
needs.
So
And Mark, how do you feel about investing in space stuff? I mean, Zeno is obviously one of the portfolio
Well, I
companies.
think it sounds like we should just invest in Dawn. Sounds like we should just invest everything in Dawn and then go home for 10 years because it sounds like they're going to be the Cisco and they'll probably be like 1,000x from here.
Probably a good
I mean,
idea.
yeah, that's a good question. I think there's probably, like Stefan was saying, so many applications that we don't really even understand or are hard to fathom. Like, yeah, like the manufacturing space or like the mining in space, where you have like so many more resources in space than you have on Earth, much easier to mine them. You don't have to deal with all kinds of environmental issues of mining from here, right? And because the end of the resources are there, then you might as well manufacture there. You don't need to bring anything down. And then it's like, well, maybe then you just actually move the people there because it's like, well, why bring it back to Earth, right? And you can sort of see how, yeah, I mean, Jeff Bezos has this whole like idea around these big satellites that are like, I'm sure you've seen these, right? And there's like sort of like cylindrical and they kind of spin to create gravity and then they have like some kind of power source in the middle and people like live on the edges and they just spin securely and you just live out in space. And yeah, I don't know. Like, I mean, that could be like, right? That could be bigger than all of the stuff we have on Earth.
Yeah, exactly. Like I think it's like the orbital reef concept.
Yeah.
Yeah, but it's so hard to know at this point. But I think it's pretty undeniable that space will have a dramatically increasing impact through our lives. Like it's just hard to imagine 2100 space just totally fizzled and humanity didn't care about going to space anymore.
But actually, when you think back, well, unless we like destroy ourselves with nuclear war, from the kind of Apollo like moment and through like the space shuttles, and at some point like there was a sort of like that's why Elon Musk started SpaceX, right? Because sort of not a lot of innovation. There was like kind of I think a dearth of I don't know whether there's interest or kind of progress, but there was a period right before he started SpaceX where not a lot of stuff was happening there, right? Like what?
Yeah, that's true. Like there's definitely been because space was so government run, like the incentive structure I think in space didn't really work, and through the big primes, like that, they're not really well incentivized to innovate. Their middle management's certainly not um, incentivized to innovate, and the frontline engineers would often get heavily penalized if they would innovate. So what we actually had was like there were a bunch of innovative organizations like DARPAs or whatever who would put out contracts for like those spaceplane contracts, like develop this spaceplane for us, please, or Phantom Express or DCX are ones that you can pull up and look at. Great examples of projects that were essentially killed either by politics changing at the time and deciding that, you know, the previous administration had started this project, so we should kill it, or the project being won by a big company like a Boeing and then run for about 3 years and just intentionally killed and said, nah, it's not feasible. But they only won it so that somebody else wouldn't win it and make it successful because that would have hurt their business, right?
Damn.
So the
It's like when
Yeah,
they're
so if it's
worried
like
about
government controlled, then it doesn't really work.
yeah, exactly. Like that they don't want to hurt their own business by
So
developing.
do you find that it's easier to operate from New Zealand because you have much less competition and much less of the sort of I don't know. Yeah, is it easier?
I think that's just being a startup means that you don't have this baggage with you.
I see.
That's why SpaceX was able to do it,
I
because
see.
they didn't have an existing business to lose.
But do you find an advantage to being in New Zealand?
Definitely in terms of like the airspace and the geography, yeah, like huge. Best place to develop high performance aircraft in the world by a long shot.
Because it's just so much easier to launch?
Yeah, so much easier to get airspace, so much easier to work with the government to get licensing. Still really great, innovative culture. Still like very, very capable people.
What about in terms of customers and talent?
Well, space is a pretty international business anyway. So like these people move around.
Uh-huh.
You have to be internationally focused anyway. Like, yes, we have to be very active in the States, and that is a barrier. But having a large part of our company in Europe means that we key in really well to the European market. That's a pretty good, well-established market. So that's kind of our customer stronghold. But US commercial companies are getting more and more familiar with buying from overseas vendors anyway.
Have you thought?
Yeah, like that's something that we intentionally approach because we know that is an additional barrier that we have to get over. But we have so many advantages out of it. I think on net, it's still a big advantage. It's why companies like Rocket Lab still have a big New Zealand presence.
Have you thought of because Rocket Lab USA now, right? Like when they went to the SPAC. Have you thought of doing that? Like moving the headquarters or like making it a US company?
Yep. Yeah. We've thought about that. There might be a time and a place for that, but it's not just yet.
What are the pros and cons of that?
Once you become a US company, like lots of if you have the IP there, lots of it becomes harder to export to the rest of the world. Not impossible, but definitely harder. But you become US export controlled. Like lots of your stuff then falls under ITAR regulations. So like we still have international regulations that we fall under now. So it's not that we just totally freely export anything anywhere now, but it just becomes tighter.
Got it. Interesting. Okay.
Cool. I'm going to cut Mark off here because otherwise he's going to ask more like 300 more questions. But maybe for final question, we always ask our guests, like, what's your advice for people who are maybe like, let's say 18 to 25 in Australia and New Zealand who are trying to figure out what they want to do with their life and potentially build a company? What would you tell them?
Just build a lot. Build whatever you're passionate about, be it software or hardware or out of wood, out of metal, out of whatever, it doesn't matter. Just start building and actually doing stuff. It's like the one common denominator in all the people that we like employ, everyone that I encounter is it's not like, yes, for sure, degrees and qualifications will help. I don't want to bag on them too much. They really do have their place. But whatever it is that you're passionate about, the more you do it, the better you get at it. And in this day and age, there's almost no excuse for not starting early. There's so many resources online about how to do stuff and how to get busy. Mm-hmm. Yeah, build.
So maybe if you were growing up today, instead of building a trebuchet, you build a rocket in your backyard.
Yeah, maybe.
You're not allowed to launch it, Mark. We told you.
Well, I don't think that would stop Stefan.
I was pretty happy building the trebuchet. I'd be happy doing that again.
Oh yeah.
No regrets there.
Cool. Well, thank you so much, Stefan. This was great. Congrats on what you've built so far. It's really amazing. And yeah, we look forward to following your journey from here.
Yeah, awesome. Yep. Thanks very much for having me.
Thank you so much.
Yeah. All right, cheers.
Thank you for tuning in to TechMates. If you enjoyed this episode, be sure to subscribe, leave a review, and share it with friends. We'll be back soon with more stories of Kiwi and Aussie founders reshaping the future and disrupting down under. Until next time, keep dreaming big and daring to disrupt.